We'll go ahead and get rolling. Good morning, everyone. Welcome to the CME Sales Monthly Webinar Series. I'm Jeff Butler, the Technical Manager here at CME. Today's webinar is titled Superior Wireless Communications for Industrial Internet of Things Applications. Presenter today is John Pipkin. John is an automation, drives, and control specialist with CME out of the Tennessee area. John spent his entire career in industrial automation. He's been on board with us now for just a little over a year. Just a few housekeeping items before we start. If you have questions during the webinar, please submit them using the control panel tool on the right side of your screen, and we'll address them at the end of the session. If you don't see that tool, there should be a red horizontal arrow. Click on that, and that should open up that little dashboard so you can see it. Everyone who's registered for the webinar will receive a link to the recording. So if you wanted to go back and look at something later or share it with somebody else, you can do that. Please be sure to attend next month's webinar, which is hosted by Steve Wright. He's one of our safety specialists here at CME. His topic will be Programming and Configuration Guidelines for Siemens Safety Advanced. That webinar will be hosted on April 13th at 10:30. I'll now turn over the webinar to John.
Good morning, everybody. As Jeff said, my name's John Pipkin. I'm the Automation Drives and Control Specialist out of Tennessee. One of the Southern guys here with CME. Today we're going to be talking about primarily the DXM100 controller. To initialize this, we'll talk about a little bit of basics of banner wireless just to tie it into the current system, an overview of the DXM100 controller, applications of the DXM100 controller, and the DXM100 controller configuration software tool. So we'll begin with the basics of banner wireless products. So I guess a simple question, what is wireless? At least from a banner engineering perspective, it's bidirectional radio communications. It's a proprietary secure network, provides coverage from feet to miles, offers a radio link loss monitoring in case of lost signal, and comes in 900 megahertz or 2.4 gigahertz frequency bands, which are considered ISM. So this is open market frequency bands that don't require any kind of licensing to use. Primarily with the banner wireless, we're talking about transmitting of signal information, whether discrete, analog, temperature being RTD or thermocouple, or some industrial communication protocols we can also do. So let's start off. What banner wireless is not? It's not Wi-Fi. It's not used to connect the PC to the internet. It's not really high speed, at least as compared to PLC I/O that's updating in milliseconds. So we're talking about signals happening in 1 to 2 seconds. It's not designed for large amounts of data. What banner wireless is, it's used for wire replacement. So wherever you would have a wire, think of an analog signal from one sensor to a PLC, you could use this to bring the analog into a wireless node and bring it in wirelessly over to a gateway to be used in the PLC. It is for wireless data transmission of discrete and analog signals, and it provides reliable data. I say slow in parentheses. We're talking about communication times up to 2 seconds, depending on the size of the network. We'll talk more about latency coming up too. And then also there's some specialized hardware specific to serial network over wireless, and then there's some Ethernet too. But again, the Ethernet is not Wi-Fi. It's basically a cable replacement. So if you want Ethernet from say a drive to a PLC, conceivably you could use this Ethernet wireless to fill that void instead of having a cable. So some basics of banner wireless are gateways and nodes. A gateway is the wireless network master. So you'll have one of those per network. And then a node is going to be a network slave device, which you can have one to many of those in the network, depending on what you're doing. So again, we talked about the ISM band, industrial, scientific, medical. These are bands predefined by the government in this 900 megahertz and 2.4 gigahertz range. Frequency hopping spread spectrum is a technology that Banner uses. It's a commonly used wireless scheme. But if you look at the graph at the bottom, basically in that 902 to 928 megahertz range, you've got 27 different bands. It divides the data into chunks. I wouldn't call them packets, but chunks spread across that frequency band and those different amounts of data. And this also, these frequency, what is called hopping, jump around in that. So there's also something called a hop code that the gateway and the nodes have to know this hopping pattern. Okay. But frequency hopping spread spectrum gives you high average power level, transmits further than other wireless protocols, and it's higher in noise immunity because obviously you're skipping around in these frequencies. So if there is a noisy area, it has the ability to skip those bands of frequency. Another networking term, time division multi-access. And again, if you look at the chart at the bottom, you've got 15 different radios or 16 different radios, 0 being the gateway. TDMA means the gateway controls the communication wirelessly and goes in sequential order. Asks number 1 for information, number 1 sends back information, asks number 2 for information, number 2 sends back information. But this means only one radio is speaking at any given time. So this, I wouldn't call it deterministic, but it's almost deterministic in giving it a means of directing traffic and only allowing one, so there's not any crosstalk, there's not any radios talking over each other. Another topic or term in Banner Wireless is binding. Binding is when you bind a node to a gateway, and this shares network information between the gateway and the nodes so that they're only allowed to communicate with each other. This also transmits that hop key as well, as we talked about. And then there's something called extended addressing, which basically ties all the nodes and gateways into one bound network. And they can only talk to radios in that bound network and not radios outside of it. So if you've got 2 gateways tied to different nodes or bound to different nodes, then they only talk to those nodes. Site survey. Built into every Banner gateway is the ability to do this site survey. And basically all that's doing is breaking down the signal between the gateway and a single node. You have to select which node you're doing this to. And basically breaks it down into green, yellow, red, or mist packets. Again, that sums up to 100%. And this cycles through these. But basically, you can put a gateway where you need the gateway and take a node at different places to make sure or double check your signal strength. So basically, this feedback is greens are greater than minus 90 dB, which is a strong signal. Yellow would be a little weaker signal, but still good. Red would be a weak signal, but still receiving data. And then missed packets are just packets that totally get lost. As it says here in the definition, minus 104 dBm of signal strength. Basically, in looking at these, a good rule of thumb is to keep the missed packet average at less than 40%. When the network misses more than 40% of the data packets, the signal is usually too unreliable or obstacles may be interfering with the signal. And basically, a missed packet means it doesn't really mean you missed the data, but it has to retransmit. So that adds more time or delay into the communication. Okay, a couple other different radio technologies that Banner uses. One is called DX80 or DX80 Gateway radio. This is for star networks. In this network, the master has to be able to communicate with each slave. So it somewhat can limit your range potentially. But again, the slaves have to communicate individually all back to the master. And this follows this TDMA architecture we talked about, where the master polls each slave and cycles through. And here's a better picture of it. So kind of from a timing standpoint, in the perfect world, great conditions where there is no required retransmission from any of the nodes. So 6 nodes to a gateway can update in 62.5 milliseconds. So that'll get you all the way around, read and write to each of the nodes. Again, this is kind of unrealistic. Typically when you're going to have some delays, something's going to have to do a retransmit. So there's some timeouts in there that can extend this, but that's kind of a typical cycle or possible cycle. All right, in this DX80 Gateway, here's a table of Modbus registers. Again, each device is going to have a node address or a gateway address. So the one radio gateway, these are 16-bit, sometimes 32-bit, depends on the device, registers. So basically the first 16 registers are linked or defined, used by the gateway, and then it's going to automatically read all the nodes bound to it. And by their node address, this is the memory area that information is going to be put in. So basically every node's got 16 registers. Not all registers and all nodes are used, but those registers are defined and automatically get read into the gateway at these address locations. So basically node 1 is read into this register table. So register 17 through 24 are basically its inputs, and then 25 through 32 are the outputs that get written to that radio, and on and on. So if we jump all the way to node 12, inputs are on 193 through 200, and outputs are 201 through 208. We'll talk a little more about this when we look in the software about how to read in this information. But again, it's automatically read into this table, predefined. The second network type would be multi-hop. And multi-hop allows for repeaters, so it's more of a tree network as opposed to a star network. So it's going to allow for a repeater to be in between the master and a slave. So it can actually, master can read repeater, repeater can read slave. So it gives you a little more range, but this does not support TDMA. Traditionally in this mode, you have to have some type of master device, PLC, HMI, controlling this communications. So one added benefit of the DXM100, it can be that master, so you don't have to have that external device. So it can do this reading and scheduling of reading. So because this doesn't follow TDMA, devices can talk on top of each other if it's not managed correctly. So multi-hop network timing, master to slave time, 9 times 0.4 seconds, plus up to 8 retry counts. So with 8 retries, you could have master transmit to slave can take up to 1 second, slave back to master another 1 second. So total send receive time 2 seconds. Now that's not really a typical thing, but that's a possible thing. Usually it's going to be much less than that with fewer retries, but worst case scenario. If you add a repeater, that adds another potential 2 seconds to that. So master to repeater to slave, worst case, could take up to 4 seconds for that signal or that response to occur. So a little slower. Again, you got to look at these timeouts and plan for that, but does give you the added range. So now we're going to look at an overview of the DXM100 that kind of gets the basics of banner wireless and some of the terminology out of the way. So this is the DXM100 controller. It was released in February 2016, so it's been out about a year. Actually, some were out before that, but this is when it came out officially. So some common applications: productivity solutions, predictive maintenance and continuous monitoring, environmental monitoring. DXM100 has the capabilities of sending text messages or emails out based on conditions. It can control like visual indication based on conditions and thresholds. And it provides communication to automation system through Modbus RTU, Modbus TCP over Ethernet, and Ethernet IP. Profinet is coming or in the works, but don't really have a time frame for that as of yet. So, industrial Ethernet of Things, a big conversation lately, hot topic of industrial Internet of Things, or as the Germans call Industry 4.0, is pretty similar, but it's gaining ground. Connecting machines with analytical and business systems or sensors to cloud can improve product quality, increase productivity, reduce cost, increase machine runtime and efficiencies. So we'll talk about some things about how the DXM100 ties into this Internet of Things. A little bit of anatomy of the DXM100. Basically, you see on top, white plastic cover. Actually, the cutout in the middle would be where an LCD screen is, and then there's also 4 LEDs that are programmable by the user. Second down, you see a cellular radio board. This is an optional board, but this can support cellular radios. You've got the processor board that you can see there, a USB port, an Ethernet port. Also has a slot for an SD card that actually comes in the DXM100. Next down is the multi-hop or gateway DX80 Gateway board. So you have to choose which radio you want in this, whether it be a multi-hop network, wireless network, or the DX80 Gateway. And then at the bottom is the DXM100 I/O board. So this is where your built-in I/O on this DXM100 exists. So look at some of the features of the DXM100. Again, on the left, we see the automation system, whether that's an HMI or PLC or cloud, some type of historian. So in the middle, we've got connectivity, which could be wired or wireless. So obviously, it's controlling the banner wireless network. There's a USB port, as we said, Ethernet port, possible cellular or optional cellular. Then there's also RS-45 master and slave. Again, the Ethernet can talk some automation protocols, Modbus TCP, Ethernet IP, also Modbus RTU. We can do internet messaging, which is pushing data to the cloud, local data logging, this SMS text and emails, and there's an HTTP API built in. Logic controller. There are some action rules you can do. You can do some scripting, and then there's a scheduler built in too, based on time of day or day of month or day of week. Also onboard I/O, analog in the 4 to 20 or 0 to 10 volts, PNP or NPN discrete inputs, counters, temperature inputs, potentiometer inputs, and this user interface, LCDs, and some, again, 4 LED indicators. A little bit about the architecture. Everything in Banner Wireless, or at least from an I/O standpoint, is based on Modbus communications. So the DXM processor has local registers in Modbus slave ID 199. These local registers can be integers or floats, and there isn't a range for non-volatile. So basically everything passes in and through these local registers. So you've got this gateway or multi-hop radio that brings in at Modbus ID 1 that brings in all the radio network, and you need to read that into the local registers if you want to do any kind of massaging of that data. Also, you would bring in the local I/O into local registers, pass from those local registers out to the LCD. And again, the action rules and the read-write rules and ScriptBasic, we'll cover more of that coming up, but that's all working with the local register data. Then also from these local registers, you can send out Ethernet, RS-232, this RS-45 as a master or a slave, and then USB mainly used for programming. Here's the integrated through cross radio. Again, we said it can either be this DX80 gateway or a multi-hop. These can work at 1 watt at 900 megahertz. There's actually a 250 milliwatt also in the 900 megahertz range, or 65 milliwatts at 2.4 gigahertz. So this is compatible with all existing Banner wireless products. So any wireless products to date that's been out 10 years or so can still work with this DXM100, the new generation. Again, we said there's a wired RS-485 interface, so you can bring in wireless Modbus device, wired Modbus devices directly into the DXM100. Again, you got an Ethernet port, a USB port, and this RS-485 Modbus slave port on board. Protocol converter functionality. The DX80 wireless, you can actually convert the DX80 wireless signal to an Ethernet protocol in this DXM100. Supported automation protocols are Modbus RTU, which is serial 232 or 485, Ethernet IP, and then Modbus TCP. Here's a quick snapshot of the DXM Configuration Tool. We will go in pretty detail at the end of this into that tool. So some of the DXM control capabilities, kind of as an overview, there is a control functions that compromise. There's a rules engine, a simple scheduler, and this text-based script language. So what this allows you to do is it helps you enable systems and solutions, but it's not a PLC replacement. This is to do simple decisions. If this is on, turn this light on, for instance, or if this is above a certain level. We'll talk about tank levels coming up too. You know, if tank level was at a high level, maybe turn on a yellow light. It's at a high level, turn on a red light or a horn to warn somebody. So it's pretty simple decisions. It's not ladder logic or anything like that. Some of the control action rules, there's some thresholds. Again, if it's above a certain level or at a certain level or below a certain level, do this. You can copy registers. There's some math functions, add, subtract, multiply, divide, average, some trending. Again, it allows emails and or SMS events based on threshold conditions to send an alert to somebody or a warning or something. And then you can generate rule-based data logs. Again, there's an SD card built into this, so you can log to that SD card on events or on certain thresholds. Scheduler is just going to be a calendar, so you can pick out, you know, a certain at 8 a.m. Monday you're going to do something, or maybe it's Friday night at the end of the shift you turn lights off or whatever. So these are just things that happen based on a given time. There's basically a calendar function. Pick the time of day, pick the day of the week for things to occur. Control scripting too is a text-based scripting language that's embedded in the controller, and it runs concurrently with these action rules we talked about. Gives you a little bit of an advanced control option over some of these thresholds and actions we talked about. So again, Internet of Things, messaging functions, actually industrial Internet of Things. So it's a device-initiated data, means the device pushes information up to a cloud server, minimizes firewall issues. Nothing's coming in, it's just data going out. You can email data logs or individual events based on conditions. Send notifications, alarm, and alerts by SMS or email. One caveat to that, to do SMS, you have to have a cellular modem built in or into the unit. And then an email would also have to have an email server to host those messages. And again, we talked about automation system interface, HTTP-based API. We can facilitate DXM to server or cloud communications, and we can interface third-party internet platforms and cloud servers as well. Here's the cellular card, certified CDMA Verizon. There's also a GSM version for export to Europe. but at least for now, they're primarily focused on the CDMA Verizon. So offers direct connect to the internet, no IT hassles going through their firewall. Again, text or email messaging alerts. This is where the SMS comes in. And remote device management can occur too. So cellular connectivity, again, this is a Verizon, so you can do contracts directly with Verizon, but Sensonics is a sister company of Banner, heavily involved with these wireless products that offers another subscription-based wireless server. So they're actually almost the middleman, if you will, for the contract. So next, cloud services is a complete industrial Internet of Things solution will require a cloud services platform. So this is just some ideas of what you can send to the cloud, whether these graphs you can look at as a web page. There is a Sensonics, also has a web service. You can see here web service packages, 50,000 data points for one company or one user. Can be as little as $10 a month. And in that Sensonics website, you can build customized web pages, basically, in a cloud server. Again, here's some graphs you can create. So now let's look at some applications to use the DXM100. So here's a pretty good picture of different things you can do. There's temp and humidity monitoring, some predictive maintenance. We'll talk about temp and vibration of motors, general purpose nodes and gateways. You can actually do some monitoring that would require like an HMI to show ultrasonic level sensing, wireless sensors, remote input devices, some of these two-way call per supervisor. There's the yellow devices at the bottom is a Q45 with a built-in push button. Beside that is a 6-button push button station that's wireless that Banner has developed. And then this wireless TL70 tower light is another product. We'll look at these all in detail. So again, we've kind of broken this down into 3 different target areas. So productivity, lighting and indication, counting nodes. There's a P14, H14 counting node. This Q45BL is this push button box, if you will, wireless push button. The 6-button pendant station. And a K50U is a new wireless ultrasonic sensor they developed for tank level. Some environmental sensors that exist are temperature nodes and temp and humidity sensors. We'll look at those too. Again, we mentioned in predictive maintenance, this vibration and temperature sensors that connect easily to this wireless network. T-gauge would be a temperature sensor, and then there's some other nodes with temperature inputs, whether RTD or thermocouple, and others that allow for pretty much any analog input, 0 to 10 or 4 to 20. So the DXM controller within these applications, it controls the local wireless network. It can collect data with this local SD card or push it out to the cloud. It can send these emails and text alerts based on thresholds. It can convert Modbus to Ethernet interface for interface to control systems or PLCs. And it can connect to this cloud. First topic of productivity is overall equipment effectiveness, OEE. One product that would lend itself well is the TL70 tower light we talked about, wireless. Does include a 32-bit counter, high-speed counter there up to 10 kilohertz. And then there's some flashing patterns you can do based on different conditions. And these can be controlled by the DXM or from a PLC. Lighting and indication, whether it's a call for parts or service or maintenance, or a pick to light, or an and-on board, process time, cycle counts, uptime, downtime, priority indication. Products, in addition to the TL70 we show, there's a K70, which uses that same TL70 base, but it's a single color LED, or the K70 Touch, again with an indicator light and a capacitive touch button on top. Also in productivity are counting nodes. In addition to that TL70 that has the built-in counter, there's this P14 and H14 counting nodes. You see the conveyor there below, so it's just kind of geared for product counting out in the field wirelessly. And again, the counter and these are within the node, so we're not updating these to the gateway any faster, but the node is keeping up with the count locally and then transmitting that to the gateway on request. So the gateway is going to have a snapshot of what the count value at a certain given period of time. Then also you can specify when to reset those counter values. Here's the P14 and H14 nodes. P14 is for performance or the DX80 Gateway radio, and the H14 is the multi-hop network. So this is a node that with a integrated D cell that's a lithium battery, and you can bring these devices directly in. So you've got one configurable discrete input, one configurable analog input, one thermistor input, an asynchronous counter, again that's 1 to 10 kilohertz, and one SDI input on the H14 node. There are also other what we'll call line powered nodes that you supply DC power to as an alternate to this if you want line power. Also in productivity, we got these Q45 push button nodes where you can call for maintenance or a pick to light type application or bin low. You see the picture there on the right. You would use like a bin low indication if one of those bins was empty. In addition to that, there's a fairly new product, this 6-button pendant, which has 6 buttons built in. Each button above it has 2 LEDs, one green, one red for indication. Next, for productivity, we can look at tank level monitoring. I guess it could also be considered environmental, but from a production standpoint, this is a black Q45 node, and then it's wired directly into this K50U ultrasonic sensor. So the two as a group is actually what we're talking about. So 300 to 3,000 millimeters, and easily screws into 1.25 MPT thread housing for easy installation. And then you've got a battery powered wireless node for quick and easy measurement of tank level. This is good for portable tanks, so you can, put this in or remove this from a tank, put it in the next tank. So from an environmental standpoint, there's temperature nodes. There's a nodes with thermistors or thermocouples or RTD inputs. And then there's a temp and humidity sensor. If you look there at the bottom left, or actually the right-hand picture also shows a DX80 node with this temp humidity sensor. So a couple different flavors of this, temperature only or temperature and humidity. And then there's two different serial interfaces, depends on the network. Mainly the one-wire serial you're going to use more with the DX80 network, and then a Modbus device more for the multi-hop. Just a different communication network between it and its local node. Next, we'll look at maintenance and conditioning. These vibration and temperature sensors. You can see there at the bottom of the page, there's one mounted underneath this motor. This is mainly for motor vibration. This application, it can monitor vibration between the motor, bearings in the motor, the pulleys, the belt, and then the fan, and like a air handling unit. So basically, there's some rules of thumb for this. There's actually a published document of different vibration levels, but I mean, for me, what I found out, basically, you need to go in and take a baseline. Where is it performing today with everything known good? And then, trigger some alarm or some light if you exceed that vibration level. So next, maintenance and conditioning. Again, this is the same sensor mounted directly to a motor. And again, it's the one-wire serial interface or the RS-485 Modbus, depending on the network you're using. Excuse me a second. Pardon me. Other options are a T-gauge, which is a Banner sensor for temperature. Works well with ESP14 or H14. That would be given an analog output signal. Again, we talked about nodes with the RTD, thermistor, thermocouple inputs. And then other nodes was just plain analog, whether 0 to 10 or 4 to 20. So now we're going to talk about the DXM100 configuration tool and how to bring these nodes into the DXM100 and how to do things within the DXM100. All right. So hopefully you can see that now. So this is the DXM100 configuration tool. You got tabs on top and tabs to the left. First thing is local registers. So local registers are registers you can define to use in your program or for your application. Here, my number one is a Q45Z RMS inches per second. So basically what I'm reading in is this motor temp and vibration sensor into a Q45 node. And these are, some of the things we're reading in. This ZRMS in inches per second, millimeters per second, temp in Fahrenheit, temperature in Celsius, and X-axis RMS, inches per second, millimeters per second. Next, I've got a one-time event and a scheduled event. We'll go into what triggers those. Then I've got some outputs, Q45. There's LEDs built into those Q45 nodes, and I'm turning lights on. Then we got a TL70 tower light with a white, blue, green, orange, and red LED. We can expand that and look at other things related to these local registers. We can assign units. So we'll go down here to this temperature F just to see we can assign a unit in F. We can have it signed or unsigned. We can do some scaling. Here you see I'm dividing by 20 because the raw data that comes in has to be divided by 20 to give you degrees F. LCD permission, that's if you want to display it on an LCD page. I haven't got that set up. Constant value, if you want to make one of these local registers a constant, you can go here and say it's a constant, or you can actually set it up as a timer. Cloud settings, if you want to send the information from this local register to the cloud, you would have here to enable cloud reporting. And then if you got any kind of permissions to the cloud, read, write, or read and write, you can set that up here. See, logging and protocol conversion. Here you show I'm saving it to a log file in the SD card, name log file 1. Okay. Then we got protocol conversion. If you want any of these local registers sent out to Ethernet IP or brought in from Ethernet IP, this is where you would assign it. So this is something brought in from the wireless network. We want to send it out to Ethernet IP. So I selected DXM to originator. If you're coming in from the PLC into local registers, you would do Ethernet IP originator to DXM. Okay. And then there's some timeout parameters if the host system doesn't respond that you can do some some fallback settings. If there's outputs you want to leave on or turn off or force on when you lose communications, you can do that through this setting. Next tab under local registers is modify multiple registers. And basically you can see here different things that you can change. You can start at register number, whether that's 1 through whatever, and ending. Here I've got a name change, so I'm creating tags or local registers called PLC_N_, and I'm incrementing by 1. So we can go back over here to 100 and see that I created, by doing that one selection, created this tag or register PLC 1, 2, 3, and 4. And again, here in this local register, we can come and give a tag a name based on whatever we pick. My tag. So then you can use it and see what that is elsewhere in this configuration or parameter file. Put it back to none so I don't forget what I've done. Again, we can enable any of this stuff within that local register. So here we got protocol IO to change. So you can do none or reset or change. Reset will go back to factory defaults. Change is going to set it to whatever you select. Next tab, we've got local registers in use, which is very handy to come in and see. I may have registers created, but don't know what all they're used for because you can use them multiple places. So again, this ZRMS inches per second, there's no units assigned to it. It's not a signed register. It's not a constant or timer. Cloud reporting is turned on. It's not allowed to be written or read on the LCD. It's set up for read-write to the web. Again, we got protocol conversion we looked at. It's writing to log file. And then there's some thresholds we'll look at coming up. Protocol conversion is going to show you just a table of those registers we looked at that we assigned this protocol conversion or assigned to Ethernet IP. And here's the register number and then what their register name is as well. And then there's an export to CSV that will export these that you can bring back into your Rockwell PLC for tag names. And there's also an ESD file we can get to bring in, I'm sorry, EDS file, not ESD file. I thought I misspoke. To bring that in easily to the Rockwell PLC world. Next tab down to our left is register mapping. Again, like I said earlier, we have to bring things into these local registers to do any of these other rules or actions or onto those tags or registers. So read rule, we see here we've got a Q45 vibration and temp node. That's what I called it again. I named that read rule from slave ID 1. Again, we talked about the DX80 network earlier. On the DX80 network, as opposed to multi-op, each thing gets read in from slave ID 100, or at least any of the wireless information. We're reading 6 registers, starting at register 33. So earlier I showed a table of Modbus registers. Node 33 is the first address assigned to node 2. Okay, so I'm reading 6 registers in from node 2, and I'm writing them to local registers from 1 to 6. And then here's the names assigned to those local registers in this table. From here, you can also assign what you're bringing in. We're using holding registers. Frequency is how often you want to read those into the DXM100. Scaling, if you want to scale those here. Or, as I showed before, you can scale them in the local register itself. Error conditions. If it's floating point and you want to swap words, you can do that here. So those are different ones we're reading in. Write rules, we're taking local registers and sending information out Again, whether that's to the wireless network or to other devices, those things we showed Modbus addresses of earlier. So obviously lights are output, so I'm writing information out to those. Here I'm writing 4 local registers from local register 9 through 12 to slave ID 1 again at 41. 41 would be the starting of the outputs of node 2. So that's how those get transmitted. Next tab down, we've got some action rules. Action rules here are thresholds so that things happen. So here we go. When local register number 30, here's the name of the register, equals a value of 1. Then we set local register 13 to a value of 1. Basically, all that's doing is when register 30 is equal to 1, then we write a 1 into this register 13, which turns on this TL70 white light. Okay. Next tab's register copy. All that does is allow us to pick a register, local register, and move it into other registers if you need to do other things with that same information. Math logic here, we can create a new math rule. Again, we can give it a name, whatever we want. Operations are add, average, sum, subtract, multiply, divide, and then there's some logical or, not and, XOR, exclusive or, not, or and. Different instructions we can do bit level within those registers. So basically add local registers. So we can do add local register 1 and 2 and send it to, I don't know, we'll say 120 just because it's something we're not used. So that's how you would do that. Again, for like an average, you can do a through, and you can do multiple registers, not just 1 and 2. So we can do an average, or we can do a sum the same way. Okay. So again, we've got these 2 buttons, add math rule to add a new one, or delete. I'm just going to delete that because I don't want to mess up my configuration that I'm using. Next tab is trending. So this allows us to do a trend. Basically, a trend is going to give you, is going to record an average value of that, a minimum value, and a maximum value. So averaging kind of a range. It's not really a trend like you would think of as a graph, but it's just going to record that information. Sample interval we can set up. So I've got this every 10 seconds. There's some filters built into. Honestly, I don't know what those do individually, but typically no filter works. So that's for action rules. Next we have scheduler. Here again, scheduler allows us to give something, I call this 8 a.m. signal. So register 8 is a register I created, a local register, and I called it scheduled event 1. So you can see the days that are highlighted. I'm going to turn off Monday, enable Monday, whether they're grayed out or highlighted. So I'm starting it with a value of 1 at 8 a.m. and I'm turning it back to 0 at 8:05. Okay. Next, we have on-time events, which happen. So we can trigger those at a specific time, no matter what day of the week. Then we can set up custom holidays. So the one-time event happens one time only. So, I've got this here, March 27th at 10 a.m. Turn on register number 7. Okay. So again, weekly events happen concurrently or repetitively based on these days of the week and this time of day. One-time events happen one time and one time only. Then we got some custom holidays if you want to make certain days holidays and do special things. Okay. Register viewer. I'm going to come up here to my device, go to connection settings, and I'm going to connect over USB. And then we can say start register 1. I'm just going to bring up a few registers we can look at. You can do a read register, which triggers a one-time read of those registers. Or you can enable polling, begin polling. So every 1 second, it's going to update those values. So good way to do online troubleshooting and see what's actually going on in the radio. I'm going to stop polling. Here we've got local registers are the ones we're bringing in to that local register list, or you can look at, nodes directly if you know the address of them. The right-hand side of that is write registers. Sometimes you want to write values into registers, and this lets you do this, again, as a troubleshooting tool for you to use. So settings, we got a general tab. General tab allows you to set the time zone. You can synchronize the time in the DXM100 with your PC. There's some GPS. If you got the cellular modem, you can actually track where your GPS location is. Modbus master communications, this is where you come set up your baud rates and your data. And then Modbus slave communications, this is where you set up there too. Cloud services, if we had that set up, we can select whether that's Ethernet or cell connectivity. If we pick cellular, there's some information there about our cellular connection. Cloud push interval, how often you want to update or push to the cloud. Port numbers, port 80, that's going to be your HTTP. So that's usually wide open. Here you can require authentication to your server. You put your server IP address, or name, or page. And then if you want to use secure HTTP, you can select that there as well. Okay. Next is logging. Logging, we can refresh our list, and this shows us what log files are on the SD card. We can select one of those and hit save, and that's going to save it onto our computer somewhere. We can give it another name. So here's some data configuration. HTTP logs are only used when you're using the cloud. If you're pushing information to the cloud and that communication link is broken for some reason, it'll log that locally to the SD card in this HTTP log. Here's where you can say when to clear it. Never, daily at midnight, 3, 7, or 10, every 3, 7, or 10 days. Okay. Event log is a separate log file that starts recording based on only log when register, whatever. We pick a register is greater than 0. So we can define a register so when some input comes on or some value comes in, we'll start that event log. Here's the name of the event log, so you can give it a custom name if you want, how big you want that event file to be. To the right, when full, we can either stop logging or save this to a new folder. We can also set up here to email this log file based on this event too. Okay, so here's where you would put whoever's email address, a subject line, and then a short message to explain what that is. Below that, we got our data logs 1, 2, and 3. When we went back to our local registers, real quick, we'll look at SD card logging, and that goes into which of those files, 1, 2, or 3. So back to settings. So in our logging, here's our 3 different data files. Again, we can give them a name. They're saved as a text file. How often you want them to update. I've got this to update every minute. Log file header style, so we can do a text or an XML or a JSON file. Not sure what that is, honestly. Max file size is 100. I did see a recommendation if you're going to email these, try to keep that max size to 50. Here's a threshold, only log when register 1 is greater than 0. Again, when it gets full, we can either stop logging or save it to a file. And when it's full, we can trigger to send an email to certain recipients with a subject line and a message of our choosing. So that's going to be the same for log file 1, 2, and 3, but that just allows you to save different log type information in different files. Scripting tab is where you would create your script file. You can actually create it offline in a Word editor and then bring that in. Some ScriptBasic options as well. Haven't done much with scripting to date, but that's where you would bring that in. Networking is where you'll come in and set up your IP address of your radio, whether that's static or DHCP. You can set up some cellular information or Ethernet also in this tab. Mail and messaging is where you set up your mail server. Here's where you can set up your list of mail recipients too. So you got 10 emails and 10 SMS recipients to set up here. Next tab is administration. That allows you to create a login password into the DXM so you can't modify anything without that password. And then bootloaders for firmware updates and such. Then you got a notes tab. So there again is our DXM tool. And then Banner Wireless supported by your C&E automation specialists that are scattered throughout the territory. And that for now concludes my seminar. Any questions, Jeff?
John, I had to unmute myself. At this point, we don't have any questions. If anybody in the audience has questions, please go ahead and type those into the control panel, and we'll wait about a minute to see if anybody has any questions that John can address for you. And if we don't hear anything, we'll go ahead and end the webinar. All right, I don't see anything coming through. Just a reminder to everyone that's still on here, you will receive a link. You'll get an email that has a link in it to allow you to be able to access the recorded webinar that John just did if you need to come back and review something later on. So, John, thanks for your work in the webinar. Appreciate it. And, oh, here's a question came through. Question, John says, do the nodes and sensors alert for low battery?
Yes, there is actually, if you're doing a battery, there is a low battery indication, but typically you want to put those on a regular replacement schedule based on the frequency of, I mean, there's some calculations we can do for estimating battery life, but typically you want to put those on a PM schedule. So, you know, once a year, once every 18 months, something like that, you would go ahead and replace those batteries.
John, we had another one come through here. It says, if we want to use Microsoft Azure Cloud, to relaying, gathering messages, etc., do we still have to use cellular connectivity?
If it'll communicate to that, I would say not. I mean, because, yeah, you can push data to the cloud either through the Ethernet connection, provided, you know, all the firewall settings are correct, or through cellular, either way. The only thing you have to have cellular for is if you're sending SMS messages.
Thank you, John. All right. What's the typical life cycle of batteries? What is the scheduled maintenance cycle?
Again, life cycle battery is hard to say without knowing what the application is. Most of the battery powered nodes have the ability to go into kind of a hibernate mode and then power up from time to time and send that information. When they're powered up, then they kind of go back to sleep. So it's highly based on frequency. Signal strength, is it 900 megahertz or is it a 2.4 gigahertz, which I didn't talk about a lot. The 2.4 actually allows the batteries to last longer because it takes less power to transmit. So, but rule of thumb, about a year. Again, it could be 2 years, could be 3 years if there's infrequent updates or less frequent updates. Is it once a minute? Is it once every 10 minutes? Is it once an hour? That kind of depends on the process and how you need to set this up. Honestly, we recommend line power nodes when possible, but the batteries are there if you need them.
Yeah. And I think Banner will certainly help out with calculations on that if you're trying to determine battery life and so forth.
Yeah, I didn't really go into that today. I was trying to focus more on the DXM100 side of it than really the nodes. So,
John, we have a question here about the cell network. It says, when using the cell network, can we use prepaid phones that use CDMA, or are we required to use Verizon?
I honestly don't know the answer to that today. I would assume, based on my knowledge of other radios, that yes, you could use, as long as it's a CDMA network, you could use a prepaid card, but I don't know that absolutely.
Rick, we'll get an answer. We'll get back to you. And let's see, question here concerning, this looks like along the lines of the signal strength. How can the individual nodes, how far can the individual nodes be from the gateway and still have good signal integrity?
Something else I didn't really go into is antenna selection. So Banner also has some other antennas. Most of these come with these, like in the picture, what we call the rubber duck type antennas. Those typically, if you're talking 900 megahertz at 1 watt signal strength, clear line of sight, a mile, they can actually go clear line of sight again. So think about clear line of sight, you can see across. And, Banner's based in Minnesota, so it's a lot of flat farmland, if you will. So they can do up to 6 miles clear line of sight. No trees, no obstructions. Typically in a manufacturing facility where you've got these radios maybe in a panel or mounted on a column or in a wall, a few hundred feet commonly. But that's why we want to come and it's really important to do the site survey to understand the signal strength you're receiving based on obstructions that you really can't account for.
Absolutely. And C&E has hardware, so if you have an application in mind, we can bring hardware out and kind of do some site surveying there.
Yeah, and again, we've got 7 automation specialists that scattered throughout the C&E territory. All of us have Banner wireless equipment, can easily come out and do the site survey for you to help you understand the true signal strength. It's hard to account for all the different noises and through walls and that stuff in factories.
All right, John, another one here. How many analog and digital I/O does the DXM100 have on board?
Let me look that up because I don't remember top of my head. So I've got one in front of me. It's got 4 universal inputs, 4 outputs, 2 analog ins, and 1 analog out. Built in. At least that's the standard DXM100. There actually is a DXM150 that has a little bit more than that. There's also a DX85 that you can easily, that would be a wired Modbus slave that you can easily hook up to the DXM100 to give you 16 configurable, whether inputs or outputs, digital signals.
A question here concerning bearing type of information. Where can bearing type information be inputted?
I'm not sure what that question means. You don't really define bearing type. If you're talking about temp and vibration of the motor, you don't really define. So I know there's a high-level vibration analysis equipment out there. This is not that. This is more of a check engine light. There's something going on. come do that higher level vibration analysis on the motor.
Right.
It's based on the same technology, but all this is looking at is an RMS value of vibration. Those other monitors are going to give you some peak levels and some analysis of exactly what the problem is. All this is going to do is say, hey, we've got a high vibration occurrence. Come check it out.
Another question concerning cell networks. Is there an app for controlling I/O by way of the cell network?
No, there's not one that exists today. Again, that could be potentially built into a custom cloud network, but no, the Banner doesn't have an app to do that.
Right. Well, John, I don't see anything else coming through. So thank you, and thank you everyone for attending. And so you get a chance, come back next month and learn about the Siemens Safety PLCs from Steve Wright. Thank you, everybody.
Thank you.